Hello and welcome to today's talk about the anisotropic spectral cutoff estimation under multiplicative measurement errors. My name is Sergio Miguel and I am a PhD student at Heidelberg University under the supervision of Jan Johannes. I will use the following 10 minutes to introduce the multiplicative measurement error model for multivariate random variables and propose a density estimator based on the estimation of a Mellin transform and the regularization of the inverse Mellin transform via a spectral cutoff approach. From there, we will derive a fully data-driven estimator using a Golden-Schluger-Lepsky method and present an oracle inequality. In the multiplicative measurement error model, we observe a random vector y consisting of a random vector x whose entries are multiplied by an error term u. More precisely, we consider the case where x and u are two positive random vectors, where x possesses a Lebesgue density f and u a Lebesgue density g, and where x and u are stochastically independent. For this talk, we focus on the estimation of the unknown density f based on an IID sample of the random vector y. Due to the independence of u and x, we can state that y possesses a Lebesgue density given by Fy equals the multiplicative convolution of f and g, which is defined as the integral over r plus to the power of d Fy divided by x gx x to the power of minus 1 dx. Here, y divided by x denotes the component-wise division, and x to the power of minus 1 equals the product of the multiplicative inverse of each entry of x. The line under the exponent shall emphasize that this term is a scalar and not a vector. We will use this relationship between f and fy to construct our density estimator. We will now present the rough construction of the estimator, while the more technical details can be found in the paper. We will use the Mellin transform of Fy developed in C and R to the power of d as the following integral. The Mellin convolution theorem, which states that the Mellin transform of the multiplicative convolution of f and g can be written as the product of the Mellin transform of f and g and the Mellin inversion formula to express f in terms of the Mellin transform of Fy. Here, all objects are well defined under certain regularity assumption on f and g. Using now the deduced representation of f in terms of the Mellin transform of Fy, one may use the empirical Mellin transform defined as the empirical mean of our data to the power c-1 plus it, and a spectral cutoff regularized inverse to define the spectral cutoff estimator f hat k as the following integral, where bold minus k in brackets denotes the hypercube induced by a k in r plus to the power of d. More precisely, the constructed estimator f hat k is an unbiased estimator of the function fk defined as the inverse Mellin transform of the indicator function of the hypercube times the Mellin transform of f, which can be written explicitly as the following integral. If we assume that f lies in the weighted L2 space, that is, the weighted L2 norm of f is finite, then we can follow that the L2 distance between f and fk is going to 0 for k going to infinity by application of the Blanche-Rayleigh equality. Here the limit k going to infinity is understood for each component. In total, we can state that Fk approximates F in the L2 sense. Let us now visualize this approximation. The plot in the top left shows the contour diagram of the density F, while on the right hand side we have the contour diagram of Fk. In the bottom row, two cross-sections in the first and second direction of the graph F and respectively Fk are given. Now we raise the parameter k equals 2, 2 to k equals 4, 4, k equals 6, 6, up to k equals 8, 8. Here we see that for the first direction the approximation error seems to be very small compared to the second direction, where the error occurs to be still large. Considering the squared bias decomposition of the risk, we see that the bias is decreasing, while at the same time the variance term is increasing. In other words, we have to pay in the variance term for each improvement in the bias term, and vice versa. Letting now the first dimension be fixed and slowly increasing the second parameter, we see that this direction is significantly harder to approximate. An isotropic choice, that is k1 equals k2, seems to be unsuitable in this situation, considering the bias term. Similar effects can be observed for the variance term, motivating the big advantage of an anisotropic choice, that is, k1 and k2 might not be equal for multivariate density estimation. After we saw that the choice of the parameter k is non-trivial, let us define a data-driven choice of the parameter k based only on the sample y1 to yn. Considering the variance term, we see that it's bounded by sigma delta gk and to the power of -1, where sigma is the 2 times c minus 1th moment of y, and delta gk is the L2 norm of the indicator function of the hypercube divided by the Melling transform of the error function g. We will now propose a Goldenschler-Walewski method for the cutoff selection. To do so, let us define the estimator v of the variance term and a hat as an estimator of the bias term, where kn and sigma hat are defined as the following. The restriction of kn is rather natural and allows us to control the variance term. Given the estimators of the variance and the bias term, we select the parameter k hat as the minimizer of the sum of a hat and v hat among the set kn. We can then show the following oracular inequality. Under certain regularity assumption on g, a moment condition on y, we get that the risk of our fully data-driven estimator matches the oracular choice of k among kn, which minimizes the bounds for the bias and the variance term up to a term of order 1 over n. In context of non-parametric statistics, this term is negligible, showing that the proposed estimator mimics the behavior of the oracular choice. We finish this talk by presenting an abstract of the Monte Carlo simulation of the paper. In the top left plot, you can see the contour diagram of the true density, and on the right hand side the contour diagram of the pointwise median of all 50 iterations of the Monte Carlo simulation. Here we choose the sample size to be 500. In the bottom, you can find the two cross-sections of the Monte Carlo simulation, where the black curve is the true density and the red curve is the pointwise median of all 50 iterations. This is all for today. Thank you very much for your attention, and please do not hesitate to ask any question.